Introduction to Robotics. Robotics is an interdisciplinary field that integrates computer science, engineering, and technology to design, build, operate, and apply robots. These machines are engineered to perform tasks autonomously or semi-autonomously, often in environments that are dangerous or unsuitable for humans. The study of robotics encompasses the creation of intelligent machines capable of sensing, processing information, and acting upon their environment. It draws upon principles from mechanical engineering for physical structure, electrical engineering for power and control, and computer science for programming and artificial intelligence. Understanding robotics is crucial in today's technologically driven world, as robots are increasingly prevalent across various industries and daily life. This field continues to evolve rapidly, pushing the boundaries of automation and intelligent systems. History and evolution of robotics. The concept of automata dates back to ancient civilizations, with early designs for mechanical devices that mimicked life. Ancient Greek engineers, for instance, created intricate mechanisms like the Antikythera mechanism and early robotic figures. The term robot itself originated from the Czech word robota, meaning forced labor, introduced in Karel Čapek's 1920 play, RUR. Rossum's Universal Robots. The mid-20th century saw significant advancements, particularly with the development of the first industrial robots by George Dassel and Joseph Engelberger in the 1950s and 60s. These early robots revolutionized manufacturing by automating repetitive and dangerous tasks on assembly lines. The evolution continued with the integration of microprocessors, leading to more sophisticated control and sensing capabilities. Today, robotics has expanded far beyond industrial applications, encompassing fields like healthcare, exploration, and personal assistance, driven by continuous innovation in AI and material science. Defining a robot. Key characteristics. A robot is typically defined as a machine capable of carrying out a complex series of actions automatically, especially one programmable by a computer. Key characteristics distinguish robots from other machines. Firstly, robots possess some degree of autonomy, meaning they can operate without continuous human input. Secondly, they are programmable, allowing their behavior to be modified for different tasks. Thirdly, robots often have sensors that enable them to perceive their environment, gathering data about their surroundings. Fourthly, they possess actuators, which are components that allow them to move and interact physically with the world. Finally, robots are generally designed to perform physical tasks, manipulating objects or moving through space. These characteristics collectively enable robots to perform a wide range of functions, from precise manufacturing to complex exploration. Robot anatomy. Major components. The anatomy of a robot comprises several major components, working in concert to enable its functionality. The mechanical structure, often called the manipulator or arm, provides the physical framework and allows for movement and interaction with the environment. This structure includes various joints and links, similar to a human arm. The end effector is the tool attached to the robot's hand, such as a gripper, welding torch, or camera, which performs the actual task. Sensors are crucial for perception, gathering information about the robot's internal state and external environment, including position, force, and proximity. Actuators, typically electric motors or hydraulic cylinders, provide the power for movement at the joints. Finally, the controller acts as the robot's brain, processing sensor data, executing programs, and sending commands to the actuators to achieve desired motions and tasks. These components are interconnected and orchestrated by the control system. Period. Robot kinematics. Understanding motion. Robot kinematics is the study of robot motion without considering the forces that cause the motion. It focuses on the geometric relationships between the robot's joints and its end effector's position and orientation in space. There are two main types of kinematics: forward kinematics and inverse kinematics. Forward kinematics involves calculating the end effector's position and orientation given the angles or displacements of all the robot's joints. This is a relatively straightforward calculation using transformation matrices. Inverse kinematics, conversely, is more complex, as it involves determining the required joint angles or displacements to achieve a desired end effector position and orientation. Solving inverse kinematics often involves iterative numerical methods or analytical solutions for simpler robot configurations. Kinematics is fundamental for path planning, trajectory generation, and ensuring a robot can reach specific points in its workspace. Robot dynamics, forces and torques. Robot dynamics is the study of the relationship between the forces and torques acting on a robot and the resulting motion. Unlike kinematics, dynamics considers the mass, inertia, and external forces such as gravity, friction, and payload that influence a robot's movement. Understanding dynamics is crucial for designing control systems that can accurately predict and manage a robot's behavior, especially when dealing with high speeds, heavy loads, or precise movements. The dynamic equations of motion for a robot are often complex, involving nonlinear differential equations. These equations help engineers determine the torques required at each joint to achieve a desired acceleration or to maintain a specific trajectory. Dynamics also plays a vital role in robot design, allowing engineers to optimize the robot's structure for stability, energy efficiency, and performance under various operating conditions. Accurate dynamic models are essential for advanced control strategies and simulation. Sensors in robotics. Perception. Sensors are the eyes and ears of a robot, providing crucial information about its internal state and the external environment. They enable robots to perceive, understand, and react to their surroundings. Various types of sensors serve different purposes. Proximity sensors detect the presence of objects without physical contact, often used for collision avoidance. Encoders measure joint positions and velocities, providing feedback for precise movement control. Force-torque sensors measure the forces exerted by the end effector, essential for delicate manipulation tasks. Vision sensors, such as cameras, allow robots to see and interpret visual information, enabling object recognition, navigation, and quality inspection. LiDAR and radar sensors provide distance and mapping information, critical for autonomous navigation. The integration and fusion of data from multiple sensors create a comprehensive perception of the robot's world, allowing for intelligent decision-making and robust operation. Actuators. Robot movement mechanisms. Actuators are the components responsible for generating motion and force in a robot, essentially serving as its muscles. They convert energy, typically electrical, hydraulic, or pneumatic, into mechanical motion. Electric motors are the most common type of actuator in robotics due to their precision, controllability, and efficiency. These include DC motors, AC motors, and stepper motors, each suited for different applications based on torque, speed, and positioning requirements. Hydraulic actuators use incompressible fluid under pressure to generate powerful linear or rotational motion, often found in heavy-duty industrial robots. Pneumatic actuators utilize compressed air, offering fast, simple, and cost-effective solutions for tasks requiring less precision or force. The choice of actuator depends on the robot's specific application, considering factors like power density, speed, accuracy, and cost. Gearboxes and transmissions are often used in conjunction with actuators to modify speed and amplify torque, ensuring the robot can perform its intended physical tasks effectively. Robot end effectors, tools and grippers. The end effector is the device attached to the end of a robot's manipulator arm, designed to interact with the environment and perform specific tasks. It is often considered the hand of the robot and is highly specialized for its intended function. Grippers are a common type of end effector, used for grasping and holding objects. They come in various forms, including 2-finger parallel grippers, 3-finger adaptive grippers, and vacuum grippers, each suited for different object shapes, sizes, and materials. Beyond grippers, end effectors can include a wide array of tools such as welding torches for manufacturing, spray guns for painting, drills for machining, and surgical instruments for medical applications. The selection of an end effector is critical for a robot's effectiveness and versatility, directly impacting its ability to perform its designated role. Many modern robots feature quick-change end effector systems, allowing them to adapt to multiple tasks efficiently. Robot control systems. Brains of the robot. Robot control systems are the brains that orchestrate a robot's actions, enabling it to perform tasks autonomously or under human supervision. These systems interpret commands, process sensor data, and generate the necessary signals to control actuators. A typical control system includes a central processing unit, CPU, memory, input-output interfaces, and specialized control software. The control architecture can range from simple open-loop systems, which execute commands without feedback, to sophisticated closed-loop systems that continuously monitor sensor data and adjust actions accordingly. Advanced control strategies, such as PID, proportional integral derivative control, are often employed to achieve precise and stable movements. Modern robot controllers are also capable of complex tasks like path planning, collision avoidance, and integration with external systems. The effectiveness of a robot heavily relies on the robustness and intelligence of its control system, which dictates its ability to adapt and perform in dynamic environments. Robot programming. Languages and methods. Robot programming involves instructing a robot on how to perform specific tasks, defining its movements, interactions, and decision-making logic. Various programming languages and methods are used depending on the robot's complexity and application. Teach-pendant programming is a common method for industrial robots, where an operator manually guides the robot through a sequence of points, recording each position and action. Offline programming allows engineers to program and simulate robot tasks in a virtual environment without interrupting production, using specialized software. Text-based programming languages, such as VAL, Rapid, KUKA Robot Language, KRL, and Python, offer greater flexibility and control for complex tasks and custom algorithms. Python, with its extensive libraries for AI and machine learning, has become increasingly popular for advanced robotics research and development. Modern programming often incorporates visual programming interfaces and simulation tools, making it more accessible and efficient. The goal is to create robust and adaptable programs that enable robots to operate effectively in diverse scenarios. Types of robots. Industrial applications. Industrial robots are automated, programmable, and capable of movement in 2 or more axes, designed to perform tasks in manufacturing and production environments. They are categorized by their mechanical configuration, such as Cartesian, SCARA, cylindrical, and articulated robots. Cartesian robots, also known as gantry robots, move along 3 linear axes, offering high precision for tasks like pick and place or assembly. SCARA, Selective Compliance Assembly Robot Arm. Robots are ideals for high-speed, high-precision assembly operations due to their horizontal compliance and vertical rigidity. Cylindrical robots have a rotational joint at the base and prismatic joints for vertical and radial movement, suitable for handling parts within a cylindrical workspace. Articulated robots, resembling human arms with multiple rotary joints, are the most common and versatile, used for welding, painting, and decorating, material handling, and more. These robots significantly enhance efficiency, quality, and safety in industrial settings, reducing human exposure to hazardous tasks and repetitive strain. Mobile robotics, navigation and autonomy. Mobile robotics focuses on robots that can move and operate in various environments. Unlike stationary industrial arms, these robots are equipped with locomotion systems, such as wheels, tracks, or legs, enabling them to traverse different terrains. A key challenge in mobile robotics is navigation, which involves determining the robot's current position, localization, mapping its environment, mapping, and planning a path to a desired destination, path planning. Simultaneous localization and mapping, SLAM algorithms are crucial for mobile robots to build a map of an unknown environment, while simultaneously tracking their own location within that map. Autonomy is another critical aspect, allowing mobile robots to make decisions and adapt to dynamic changes in their environment without constant human intervention. Applications range from autonomous vehicles and delivery robots to exploration rovers and domestic cleaning robots. The development of robust perception, planning, and control systems is vital for safe and effective mobile robot operation. Human-robot interaction, HRI. Human-robot interaction, HRI, is a field dedicated to understanding, designing, and evaluating robotic systems for use by or with humans. The goal of HRI is to create robots that can interact with people naturally and effectively, enhancing collaboration and user experience. This involves addressing various aspects, including communication, safety, trust, and social dynamics. Communication can be verbal, speech recognition, and generation, non-verbal, gestures, facial expressions, or through interfaces like touchscreens. Safety is paramount, especially for collaborative robots, cobots, that work alongside humans, requiring advanced sensing and collision avoidance. Building trust is essential for human acceptance and effective teamwork, often achieved through predictable behavior and clear communication of robot intentions. HRI research also explores the psychological and sociological impacts of robots on human society. As robots become more integrated into daily life, understanding and optimizing HRI is crucial for their successful adoption and beneficial deployment. Artificial intelligence in robotics. Artificial intelligence, AI, plays a transformative role in modern robotics, enabling robots to perform complex tasks that require reasoning, learning, and adaptation. AI algorithms allow robots to interpret sensor data, make autonomous decisions, and even learn from experience. For instance, AI-powered vision systems enable robots to recognize objects, navigate complex environments, and perform quality control with high accuracy. Path planning algorithms, often leveraging AI techniques, allow robots to find optimal routes while avoiding obstacles in dynamic settings. Decision-making processes, from choosing the next action in an assembly line to responding to unforeseen events in an exploration mission, are significantly enhanced by AI. Furthermore, AI contributes to natural language processing for human-robot communication and advanced manipulation capabilities. The integration of AI moves robots beyond mere automation, granting them a level of intelligence that allows for greater flexibility, problem-solving, and autonomy in diverse applications. Machine learning for robotics. Machine learning, ML, a subset of AI, is particularly impactful in robotics, enabling robots to learn from data and improve their performance over time without explicit programming. Supervised learning techniques, for example, can train robots to recognize objects or perform specific actions by providing labeled datasets. Reinforcement learning allows robots to learn optimal behaviors through trial and error, receiving rewards for desired actions and penalties for undesired ones. This is especially useful for tasks where explicit programming is difficult, such as complex manipulation or navigation in unknown environments. Deep learning, a more advanced form of ML, utilizes neural networks with multiple layers to process vast amounts of data, leading to breakthroughs in robot vision, speech recognition, and motor control. ML enables robots to adapt to new situations, generalize from limited experience, and perform tasks with greater dexterity and intelligence. It is a cornerstone for developing truly autonomous and adaptive robotic systems. Computer vision for robots. Computer vision is a critical component for robots, allowing them to see and interpret their surroundings through digital images or video. This technology enables robots to understand visual information, which is essential for tasks like object detection, recognition, tracking, and 3D reconstruction. Object detection algorithms help robots identify and locate specific items in their workspace, crucial for pick-and-place operations or quality inspection. Object recognition allows robots to classify what they are seeing, distinguishing between different types of products or tools. Tracking enables robots to follow moving objects or people, vital for collaborative tasks or surveillance. 3D reconstruction, often using stereo cameras or depth sensors, provides robots with a spatial understanding of their environment, enabling accurate navigation and manipulation. Computer vision systems are continuously improving with advancements in deep learning, allowing robots to perceive and interact with the world with increasing accuracy and sophistication, mimicking human visual capabilities. Robot safety standards and ethics. Robot safety is paramount, especially as robots increasingly work alongside or interact directly with humans. Various international and national safety standards, such as ISO 10218 for industrial robots and ISO TS 15066 for collaborative robots, define requirements for safe design, installation, and operation. These standards cover aspects like emergency stop functions, speed and separation monitoring, power and force limiting, and safeguarding. Adherence to these guidelines is crucial to prevent accidents and ensure the well-being of human workers. Beyond physical safety, the ethical implications of robotics are becoming increasingly important. This includes discussions on job displacement, privacy concerns related to surveillance robots, accountability for autonomous decisions, and the potential for misuse of robotic technology. Ethical considerations also extend to the design of robots, ensuring they are transparent in their actions and do not deceive users. Developing a robust framework for both safety and ethics is essential for the responsible and beneficial integration of robots into society, fostering public trust and acceptance. Applications. Manufacturing and assembly robots have revolutionized manufacturing and assembly industries, significantly improving efficiency, precision, and safety. In manufacturing, robots perform tasks such as welding, painting, material handling, and machining with unparalleled consistency and speed. Robotic welding systems, for instance, ensure uniform weld quality and reduce human exposure to hazardous fumes and intense heat. Robotic painting systems achieve flawless finishes and minimize material waste. For assembly, robots can precisely place small components, screw parts together, and perform intricate wiring, often outperforming humans in repetitive, high-precision tasks. Collaborative robots, cobots, are increasingly deployed in assembly lines, working alongside human operators to augment their capabilities and improve ergonomics. The use of robots in these sectors leads to higher production rates, reduced labor costs, improved product quality, and enhanced worker safety, making them indispensable tools in modern industrial production. Their ability to operate continuously and perform monotonous tasks without fatigue is a major advantage. Applications. Healthcare and surgery robotics is transforming the healthcare sector, offering innovative solutions for surgery, patient care, and laboratory automation. Surgical robots, such as the Da Vinci surgical system, enhance precision and dexterity for surgeons, enabling minimally invasive procedures with smaller incisions, reduced blood loss, and faster patient recovery times. These robots provide magnified 3D vision and tremor filtration, allowing surgeons to perform complex operations with greater control. In patient care, robots assist with rehabilitation, provide companionship, and help with medication delivery, particularly for elderly or disabled individuals. Exoskeletons, a form of wearable robotics, aid patients with mobility impairments in walking and regaining strength. Laboratory automation robots handle repetitive tasks like sample preparation, drug screening, and diagnostic testing, increasing throughput and accuracy while reducing human error. The integration of robotics in healthcare promises to improve patient outcomes, enhance efficiency, and expand access to high-quality medical services, addressing critical needs in a rapidly evolving field. Applications. Exploration and defense robots are indispensable tools for exploration and defense. Operating in environments too dangerous, remote, or inaccessible for humans. In space exploration, rovers like Curiosity and Perseverance have explored Mars, collecting data and samples, significantly expanding our understanding of other planets. Underwater robots, ROVs and AUVs, are used for deep-sea exploration, mapping the ocean floor, inspecting underwater infrastructure, and studying marine life. These robots can withstand extreme pressures and operate for extended periods. For defense and security, robots perform tasks such as bomb disposal, reconnaissance, surveillance, and logistics. Unmanned ground vehicles, UGVs, and unmanned aerial vehicles, UAVs or drones, provide critical intelligence, protect personnel, and deliver supplies in hazardous zones. These applications leverage robots' ability to operate autonomously, gather data in hostile conditions, and perform tasks that would put human lives at risk. The continued development of robust and intelligent autonomous systems is crucial for advancing capabilities in these challenging domains. Emerging trends. Collaborative robots. Collaborative robots, or cobots, represent a significant emerging trend in robotics, designed to work safely and interactively alongside humans in shared workspaces. Unlike traditional industrial robots that operate in caged-off areas, cobots are equipped with advanced sensors and safety features that allow them to detect human presence and react accordingly, preventing collisions or reducing force upon contact. This enables a new paradigm of human-robot collaboration, where humans and robots can leverage each other's strengths. Humans can provide cognitive skills, adaptability, and problem-solving, while cobots offer precision, strength, and endurance for repetitive or heavy tasks. Cobots are typically smaller, lighter, and easier to program than conventional industrial robots, making them more accessible to small and medium-sized enterprises. Their flexibility and ability to integrate seamlessly into existing workflows are driving their adoption in various industries, from manufacturing and assembly to healthcare and logistics, enhancing productivity and worker safety. Emerging trends. Soft robotics. Soft robotics is an innovative field that focuses on designing and building robots from highly compliant and deformable materials, often inspired by biological organisms. Unlike traditional rigid robots made of metal and hard plastics, soft robots can bend, stretch, twist, and conform to complex shapes, offering inherent safety when interacting with humans and delicate objects. These robots are typically powered by pneumatic or hydraulic systems, using pressurized fluids to inflate or deflate internal chambers, causing movement. Their flexibility allows them to navigate confined spaces, grasp irregularly shaped objects gently, and absorb impacts without damage. Applications include medical devices for minimally invasive surgery, wearable assistive devices, and grippers for handling fragile items in manufacturing. Soft robotics is still a relatively young field, but its potential to create robots that are safer, more adaptable, and more biologically inspired is immense, opening new possibilities for human-robot interaction and exploration in unstructured environments. Future of robotics. Societal impact. The future of robotics promises profound societal impacts, reshaping industries, economies, and daily life. As robots become more intelligent, autonomous, and ubiquitous, they will continue to automate tasks, leading to increased productivity and efficiency across various sectors. This automation will inevitably transform the job market, requiring new skills and creating new roles, while potentially displacing others. Ethical considerations, such as job displacement, data privacy, and accountability for autonomous systems, will become even more critical. Robots are also expected to play a larger role in addressing global challenges, including healthcare for aging populations, sustainable agriculture, disaster response, and environmental monitoring. The integration of robots into homes and public spaces will necessitate careful design for safety, usability, and social acceptance. Ultimately, the future of robotics will be shaped by ongoing technological advancements, thoughtful policymaking, and societal dialogue to ensure that these powerful tools are developed and deployed responsibly for the benefit of humanity. The potential for innovation and positive change is immense. Designing a simple robotic system. Designing a simple robotic system involves several key steps, starting with defining the problem and desired functionality. First, clearly articulate what the robot needs to do, its operating environment, and performance requirements. Next, consider the mechanical design, including the robot's physical structure, number of joints, and type of locomotion. This involves selecting appropriate materials and ensuring structural integrity. Then, choose the necessary sensors for perception, such as proximity sensors for obstacle detection or encoders for joint position feedback. Following this, select suitable actuators, like DC motors or servos, to provide the required movement and force. The control system is then designed, involving the selection of a microcontroller, e.g. Arduino, Raspberry Pi, and developing the control logic and programming. Finally, integrate all components, test the system thoroughly, and iterate on the design based on performance feedback. Prototyping and simulation tools are invaluable throughout this process to refine the design and troubleshoot potential issues before physical construction. Career paths in robotics. The field of robotics offers a diverse and growing array of career paths for individuals with various skills and interests. Robotics engineers are at the forefront, involved in designing, building, and testing robotic systems across different industries. Software engineers, specializing in robotics, develop the complex algorithms and programs that control robot behavior, including AI, machine learning, and computer vision applications. Mechanical engineers focus on the physical design, kinematics, and dynamics of robots, ensuring structural integrity and efficient movement. Electrical engineers design the electronic components, power systems, and control circuits that bring robots to life. Beyond core engineering roles, opportunities exist in research and development, project management, technical sales, and field service for robot installation and maintenance. As robotics continues to expand into new domains like healthcare, logistics, and consumer products, the demand for skilled professionals in this exciting and innovative field is expected to grow significantly, offering dynamic and impactful career opportunities.